Hey everyone, and welcome back to The Explainer. Today, we're unpacking the ultimate VIP of the universe, carbon. We're going to dive deep into carbon and its compounds, and we'll be sticking strictly to the exact trusted terminology you'll find in the NCERT syllabus. So let's just jump right in. Think about the hardest substance known to humanity, a diamond. Now compare that to the soft, brittle graphite inside your pencil, and then think about the complex spiral of your very own DNA. What ties all of these completely different things together? It's just one tiny versatile element, carbon. It is literally everywhere. It forms the very foundation of life, the fuels we rely on, our medicines, and pretty much all the plastics we use daily. Here is our game plan for today. We've got 6 key areas. First, we'll meet the carbon atom. Second, explore its versatile nature. Third, dive into chains and homologous series. Fourth, naming and functional groups. Fifth, reactions and compounds. And finally, number 6, soaps and detergents.
All right, section 1. Let's officially meet the carbon atom.
Carbon has an atomic number of 6. If you picture its electron configuration, that means it's got 2 electrons chilling in its inner shell and exactly 4 electrons in its outermost shell. And because it has those 4 outer electrons, it has a valency of 4. Now, rather than violently ripping away or giving up 4 electrons to achieve stability, carbon takes a much smarter route. It's perfectly positioned to just share them. That sharing mechanism, that's what we call a covalent bond. A covalent bond happens purely when atoms share pairs of electrons to get perfectly stable. It's like a molecular compromise. Carbon can share 1 electron with each of 4 hydrogen atoms to build a highly stable molecule like methane. But it doesn't stop there. It can also share with oxygen to form double bonds or even team up with nitrogen to form triple bonds. Now, because covalent compounds are all about sharing electrons rather than swapping ions, they have some really distinct, testable properties. They generally have pretty weak intermolecular forces, meaning they break apart quite easily under heat, which gives them low melting and boiling points. Plus, since they don't have any free-floating ions roaming around, they are notoriously poor conductors of electricity. Moving right along to section 2, carbon's versatile nature. So how on earth does this one single element manage to build millions of different compounds? Well, it basically comes down to 2 superpowers. The first is catenation. This is carbon's totally unique ability to bond directly with itself. It's basically like carbon atoms holding hands to build these massive, complex molecular structures. And because these carbon-carbon bonds are incredibly strong and stable, they can form endless variations like long straight chains, highly branched chains, and even totally enclosed rings. Superpower number 2 is tetravalency. Remember those 4 outer electrons we talked about? Well, this allows carbon to branch out in 4 different directions all at once. Because carbon is tetravalent, it can form stable covalent bonds with 4 other atoms simultaneously, whether we're talking about hydrogen, oxygen, nitrogen, or chlorine. Put catenation and tetravalency together, and you literally unlock endless chemical possibilities. Okay, on to section 3, chains and homologous series. The absolute crucial takeaway here is understanding the difference between saturated and unsaturated compounds. On one side, we have saturated compounds, known as alkanes. These only have single carbon-carbon bonds, meaning they are completely maxed out or saturated with hydrogen. On the flip side, we've got unsaturated compounds. If they feature a double bond, they're called alkenes. If they rock a triple bond, we call those alkynes. Now, as these chains grow, they create what's known as a homologous series. Imagine stacking identical building blocks to make a tower. When you step up from methane to ethane and then to propane, every single jump up the chain adds exactly 1 CH2 group. And with every CH2 unit you tack on, the molecular mass jumps by exactly 14 units. But, and this is the really cool part, their core chemical properties remain beautifully consistent all the way up the chain. Up next, section 4, naming and functional groups. Honestly, naming organic compounds is pretty much just a giant matching game. You simply take the prefix that counts your carbons, meth for 1, S for 2, prop for 3, you get the idea, and you combine it with a suffix for the bond type. So let's say you have a 2-carbon chain with a double bond. You take eth, add ene, and boom, ethene. It really is that simple. But let's be real, plain carbon and hydrogen chains can get a little boring. Enter functional groups. These are specific clusters of atoms that we attach to our carbon chains to spice things up. Add an OH group, and suddenly it becomes an alcohol. Throw on a CHO, and you've got an aldehyde. These tiny little additions completely hijack the chain and completely dictate the characteristic chemical properties of that compound, fundamentally changing how it acts in the real world.
Section 5. Reactions and compounds. If we're sticking strictly to the NCERT syllabus, there are exactly 4 core chemical reactions you absolutely have to know. First up is combustion. That's just burning carbon and oxygen to release CO2, water, and heat. Picture that classic blue methane flame. Second is oxidation, which is using an oxidizing agent to force oxygen into a compound. Third, we have addition. This is where we break apart those unsaturated double bonds to add in new elements, usually with the help of a nickel catalyst. And fourth is substitution, where we use sunlight to literally kick out a hydrogen atom and swap it for something else entirely, like chlorine.
Let's look at how this plays out with 2 heavy hitters you'll definitely see in the real world. First is ethanol. It's got that OH group, it burns super clean, mixes perfectly with water, and is an absolute powerhouse as an industrial solvent. Then there's ethanoic acid, which rocks the COOH group. A highly diluted 5 to 8% solution of this stuff, that is literally the household vinegar sitting in your kitchen right now. And here's a fun fact. If you mix it with baking soda, it reacts violently and releases a ton of CO2 bubbles.
Finally, Section 6. Soaps and detergents.
Soap molecules have a totally brilliant 2-part design. You've got one end that loves water and a long carbon tail that absolutely loves oil and grease. When they hit water, they form this microscopic cluster called a micelle. The oil-loving tails all point inward to trap the grease droplet, while the water-loving heads face out. That lets the water just effortlessly wash the whole tiny cluster down the drain. Oh, and keep in mind, while regular soap kind of struggles in hard water, synthetic detergents are chemically tweaked to clean perfectly no matter what kind of water you're dealing with. We have covered some serious ground in this explainer today. If you can check off these concepts, from tetravalency and catenation to covalent bonds, the difference between saturated and unsaturated, homologous series, those 4 major chemical reactions, and finally micelles, then you are golden. You have just built a massive, rock-solid, textbook-perfect foundation of carbon chemistry. You now hold the fundamental building blocks of chemistry, materials, and honestly, life itself. I really hope this run-through has shown you just how elegant and versatile carbon truly is. So I'll leave you with this provocative thought. The next time you look at the plastic on your desk, the food on your plate, or the graphite in your pencil, remember you're looking at the exact same atomic hero. Stay curious, keep exploring, and I can't wait to see what you'll build with your new understanding of carbon. Thanks for joining me on this explainer.